Welcome back. This time we are going to learn about linear regression and specifically what is referred to as simple linear regression. You have learned in the previous modules that you can use R for doing good graphics work. You learned that you can take, no matter how complex your data analytical task may be, you can actually start working with two variables at a time. And with these two variables at a time, you can draw graphs, you can start setting up table formations, routines, and stuff like that. So in this particular module, we are again going to take that simple minimalistic approach where we will take two variables at a time and learn. Except in this particular situation, both variables are continuous variables. And these continuous variables can be plotted in the form of a scatter plot, or when we statistically analyze them, the process is known as a simple linear model or simple linear regression. We're going to give, in this particular case, some data sets. We'll run you through some of the basic initial principles and build on that in the next few modules. Okay, so happy learning. Thanks.
This is the first part of two-part in which we are going to look at simple linear regression, where we're going to look at a continuous outcome variable and a continuous explanatory variable. And what we're going to learn here is going to be applicable to a number of different settings. So we start with a very minimalistic introduction to the concepts of setting up regression models in R. Now, I must warn you that in this particular modules of lectures, I have not deliberately attempted to get into the details of the nitty-gritty of the theoretical details of how you can conduct or how you can run regression models in R. You should be able to conduct many good tutorials, books, and resources in both the internet as well as take some lessons in the classrooms, etc. The focus of these exercises is mainly to showcase some very simple things that are available in R. And you should be able to refer to the resources that I have included in this package to learn more about the regression models and things like that in R. Overall, R provides you a very nice and intuitive interface in which you can get a lot of work done. Remember though, that when you work with R, you will not get detailed and copious outputs that is characteristic of some other statistical data analysis software. Instead, you will get you can store the results in the form of objects which you should be able to manipulate. If you're unsure about how to manipulate objects, please refer to the objects tutorial in this lesson, and you should have no problem in working with R and working through it. So in summary, R can understand and intuitively guide you to work with your regression modeling. So with this, let's get started and see what we have for you. And this is part of the ePathshala program. And another thing that we would like to provide is we'll get some introductory preliminary work done, and then we'll describe some principles. We'll try to give you some demonstration of the different kinds of features in R that will help you to make sense of the regression models, and then we'll summarize everything that we had learned. In this, then, we are going to learn about simple linear regression with one predictor. Now, this means that you will have one outcome variable and one explanatory variable. So one predictor variable and one outcome variable, or one, what you could say, dependent variable. Some people use that term, but we would prefer to use the term outcome variable, and we'll say one predictor variable. And both these variables, that is the outcome variable as well as the predictor variable, these are continuously distributed variables. So these are all continuous variables. So we shall learn about what happens when you use a single continuous variable as a predictor. In particular, in this module and in the next few modules, we will learn how we can use the LM function. The LM function is present in the stats package, in a very standard R package. It's a very simple function to use. And if you are ever stuck in using this function, remember to use the help files to learn more about this. And we shall also learn how we can read outputs from linear regression models in R. When I say how to read outputs from linear regression models in R, I essentially mean that you should be able to save your linear regression model outputs in the form of an object, and then you can further manipulate that object in order to get and do what you want to do about it. We shall learn about confidence intervals and predictors, and in the process you should be able to have a fairly good amount of experience or a good amount of knowledge as to what you can do with R. The rest of it, of course, you will pick up as you start practicing with real-world data. So to continue, we're going to learn simple linear regression with one predictor, and we're going to use the LM function. Right. So let's start with some preliminary ideas about data and notation. All the data that we're going to use should be in the form of data frame. So you can have individual variables, and these variables are coerced into a rectangular data frame, and we shall be using that rectangular data frame in order to run the regressions. In this particular case, we are going to use two continuous variables. One of them is going to be an outcome variable, and the other is going to be an explanatory variable. We will be using what is often referred to as the Wilkinson-Roger notification for working with linear models. Now, the Wilkinson-Roger system in which you specify regression models essentially is a very simple model. It's very intuitive. You put an outcome variable, you put an explanatory variable, and you use certain specific symbols to get the work done. It is elegant for its simplicity, and it is very useful in order to extract objects from the regression model output. In general, the convention for working with any sets of data or data analytical plan is to first plot some figures, which means that we plot an outcome variable and an explanatory variable, and there are many different ways of plotting them. In our case, we are going to put the x variable on the horizontal axis, and the y variables are plotted on the vertical axis. As simple as that. So the first thing that we should do is that we shall start with a scatterplot. A scatterplot is a plot in which dot points are plotted for each value of the x variable for the corresponding value of the y variable. Remember that in this particular situation, we are working with continuous variables for both outcome as well as explanatory variables. After those points are plotted, then R is instructed to fit a regression line. The fit regression line, of course, as you understand from your studies in statistics, is the one that minimizes the error variance. So this means that this is the best fit line of the many possible lines that will minimize the error variance around that line. And we'll take a look at the formula in a second to understand this. And therefore, when we do this, we have to be very careful because we are actually forcing a linear regression model here. It is quite possible that a straight line is not probably the best fit for the data that you have in your hand. Therefore, we have to make sure that we do understand what we are doing with the scatterplot. Even though we are forcing with a linear regression model, a scatterplot can nevertheless inform us about other modeling possibilities, which means depending on the cloud of the points you may see that a straight line model is probably not the best fit. It is quite possible to have something like a curvilinear model, like a quadratic model, or maybe some other model that can be better suited. It is also quite possible that different parts of the scatter cloud can be modeled differently, and therefore you'll have to come up with creative solutions as to how you can make those calls. Nevertheless, it is always a good practice to start with a scatter plot and then progress into other steps of regression. In general, although it is not going to be covered in this particular module, perhaps in a different module, a very good idea in general, if you've got a data frame with a number of different variables, it is a good idea to actually put together a comprehensive plot of the many different continuous variables. So out of your data, create a separate data frame that only contains the continuous variables, and then use the function pairs with no parameter inside it to actually create a scatter plot of, or pairs of scatter plots of many different variables. And so this is going to result in pairs of scatter plots for all possible pairs of variables in the data. Now, before we get into to show you the nitty-gritty of using simple linear regression in R, let us reiterate some assumptions of multivariate or simple linear regression. The first is this, that in this particular case, we shall use just one explanatory and one outcome variable for this particular session. We assume that the values of y will be independent of each other. This is a very important point you must note. That is, all the values of your variable y will be such that their probability of the occurrence is not related to each other in any way, which is a little bit complicated idea to follow, but it is somewhat different. That is, they're not. We assume that, but whether that's going to happen or not is another question. But it's not like, let's say you wanted to plot the occurrence of rainfall, and you wanted to model it, using the rainfall or humidity of a given period of time in a particular season, and you wanted to model that using a simple linear regression. That factor, that is amount of rainfall over, say, 5-day period, itself is going to violate this assumption, because rainfall today can be influenced by some underlying weather pattern. So for 5 days, the rainfall levels may be correlated. Or say, for example, daily temperature. There is a family of data analytical strategies for that, but this is not what we're going to cover here. So the question is, what we're going to do is this, that therefore, given x, y will have normal distribution or Gaussian distribution whose mean will be a linear combination of x. Now here, of course, in this particular instance, this is not going to be an issue because we are only going to use one x variable. But when we are going to use more than one x variable, that is, if an explanatory variable with some covariates, then you're going to think in terms of the fact that it's going to be a combination of the different x's. So for us, it's going to be a case of y equals alpha, which is an intercept, and beta times x, and beta in this particular case is going to mean that it is a slope of x, and the error term. So alpha is the intercept, beta is a parameter estimate of the slope along which the x is going to move, and e is referred to as the error term, which is identically and independently distributed, which means that like the y variable, e or error term 2 should not be correlated with each other. If there is a correlation, then there is a problem. If E, which is also referred to as residuals, can be seen to be varying with Y, then there is a violation of these principles. And therefore E is often referred to as random noise. And the function Lm actually estimates the alpha and the beta parameters. So for this exercise in linear regression that I'm going to demonstrate now, we are going to use some very well-known packages. One package is written by Julian Faraway, which is known as the Faraway package. It is a very, very interesting and a very important package that you should be installing in your machine and working through the data that are contained within the Julian Faraway package. Julian Faraway has also written a very nice and readable text, which I've also referenced here in the resources section on working with R. So we are going to use Julian Faraway's Faraway package. Another package that we're going to use is known as DAAG, which stands for Data Analysis and Graphics by John Maindonald, who is a professor of statistics at the Australian National University. And in the DAAG package also contains data. So what you will need to do is this, that you have to install those packages and install or call the library. So in the first line of this code, I have issued a command, or I have issued an instruction to the computer to install package, which is known as Faraway. And in the second line, we are going to install packages DAAG. Once you have installed that package, or if you have that package already installed in your computer, then please put a hash mark in front of install.packages so that you comment them out. Then you call the library DAAG. You should always also call the library Faraway. And in the Faraway library, there is a data set called PIMA, which contains information about blood sugar and blood glucose level and the tests of among PIMA Indians. And so this is our data set that we're going to use. And then you don't really have to type it in the console at the moment, but you can actually use the ALM, which is a linear model building function in R, in order to work with these examples. And if you want to know more about linear model or linear regression, then use either a question mark and then LM, or help, open and close parentheses, and type LM within quote marks. In this phase, what I call is, let's get our hands dirty, as they say. That is, let's get to do some work. So for this exercise, we shall load the data analysis and graphics package, the DAAG package. And the DAAG package, the particular one that we're going to work, is a very, very simple data set. It's known as a roller. And in the roller data set, you are actually looking at the depressions that are made on the ground when you use a lawnmower or a roller. And the roller, of course, is going to roll on, not a lawnmower, but a roller. When a roller moves on and it marks some depressions in the ground, we're going to get a sense of that. So what we have done here in these 3 lines of code is this, that we have called the data roller, having called the data library in the first place. And then we have saved the product of the linear model of depression and weight. That is depression, then we have put a tilde mark, left a comma, and then specified the data set from where they came from, which is roller. And we have saved the result of that regression model into an object which is known as roll weight. This is it, as simple as it gets. You see, R is a very, very simple way in which you can get a lot of work done. And then what we have done is this, that we would like to summarize everything that we have obtained. Now I'll show you how the summary looks like, but all that you have to do is then just issue a command to that object and say, I would like to summarize the object roll weight in which I have stored the results of the linear model. So the summary function will give you an output into the console. And let's read that output from the console. And the first, you can see that it gives you the formula, which is known as the Wilkinson-Rogers formula, where you write the model. It's a very, very elegant and very simple way to write the model. So what you do is this, that you put the outcome variable first, then you put a tilde mark, then you put an explanatory variable first, you specify the data. You can do a lot more with this, of course, but we have not shown you all of these things to keep matters really, really simple. If you want some more information, check help.lm and you can get a lot more information that way. The first line that R then puts out when you request R to put out the summary is information about the residuals, which is the E component or the error term. You can see it gives you the minimum, the first quartile, the median, the third quartile, and the maximum. I can see that there is the distribution of the residuals. And as you can see that the residuals have got a negative kind of skewness about them. So it's not exactly, doesn't look like that they may be following a normal distribution, but we can check that, our assumptions later. It also puts out what is known as coefficients. So these are regression coefficients in the form of a table. Remember that residuals, coefficients, and every other information you can obtain from the object by manipulating the object of, in this particular case, it's a roll weight object. Okay, so we have kept them in an object called a roll weight. So in the coefficients, it starts with an intercept. If you specified that you do not like to have an intercept in the model, then you preface that model with a 0 or -1, and that will omit the intercept. We'll see an example later on. So the first entry is an intercept, and then the second entry is the row-wise is the specification of the explanatory variable. The first column of that entry kind of table is the estimate of the correlation coefficients. So you see that for the intercept, the beta coefficient is -2.087. It comes up with a standard error. It gives a t-value, and it gives you a probability estimate based on this. The second line is about the weight, which means if the roller weight is heavy, then it's going to make a bigger depression. And you can see that there is a non-standardized or unstandardized beta coefficient that you get to see here, which is 2.667. So with each increasing weight in kilograms, you're going to get a 2.67 units, however that was measured, increase in the depth of the of the depressions. And you can see that this is statistically significant based on the readings, and it starts with 2 stars. And you can actually then manipulate these numbers, so you can control how many stars you want. If you do not want the stars, then put options so show significant stars, set it to false. If you want 2 digits, make it digits equal 2. If you want 3 digits, make digits equal 3, etc. I did not put any option statement here. In the final 3 lines, you get the residual standard error, and along with the degrees of freedom, you get the multiple r squared, in which case you see here they give you both the multiple r squared as it stands, or the adjusted r squared, which takes into account the degrees of freedom. And you see over here we get explained about 60% in the variability of the depth only by the weight of the roller. And you also get a sense of the F statistic for the entire model, and you can see that the model is a very robust model. By the way, the p-value corresponds to the value of the explanatory variable here. We have reversed the order somewhat, but in a real life situation, you will actually be using a scatter plot first and then move into a linear regression. Okay, so here you can see that it seems that maybe a straight line just might fit, and you can see that there is a slope that goes. It's a very small slope, and you can see there's an intercept that you can see. And you can see that there is an intercept of minus 2.09. There is a slope, and there is a p-value for the hypothesis that tests the true intercept to be 0, which means it's a flat line, and the true slope is also going to be 0. And you can see that that hypothesis is rejected, particularly the one for the slope. What we cannot reject the hypothesis that the true intercept is 0, although the intercept has shown some values. You can, in subsequent models, if you so want, can remove the intercept and then rerun the model, and so on. So once we have done this bit, the very next thing that you should do is you should check the model assumptions. And there are many different ways in which you can check the model assumptions. You can plot the residuals versus fitted values, and always residuals versus fitted values, never residuals versus explanatory variables. Normal probability of the plot of the residuals, because we want to see that the residuals follow a Gaussian distribution. And we will assume that the residuals and the fitted values should not show a pattern. In other words, we are not going to expect that the residual values are actually going to diverge from a range, which is known as heteroscedasticity. And the residuals will ideally be normally distributed. So let's see how we can accomplish these kind of activities in R. So we are going to put some codes for residuals and predicted values. So the function that we use for that is predict, and then you open and close the parenthesis, and within the parenthesis you type the object of the linear model. Remember, when we started working on this, we actually wrote the code in the Wilkinson-Rogers formula of a linear model and stored that into an object called role WT. Now we take that role WT and use the function predict in order to extract the predicted or fitted values from the from that object. We can also extract the residuals. Very simple function again. It's just resid, and then you mention the object in which you stored the linear model. One thing that you can do is you can add the predicted values, the fitted values, and the residuals back into the model. For example, if you use SPSS or SAS or some other program, then you can tick a box, and that box will you take care of this. In R, it's a two-step process, because you store everything within the object of the linear model, and then you manipulate that object using some functions, some kind of extraction process, and then you put them back into a data frame. What you can then do is you can start plotting the summary. Here is something that is very important. Look at the code which says plot, then we have opened and closed the parenthesis. We put the name of the object, which is roll weight in this case, and we have included a keyword which is called, or an option which is referred to as which equals 1. It needs a little bit of an explanation and handholding. If you remember, several modules back, we introduced you to the concept that you could plot a regression object, and the plot would then sequentially run you through a number of different plots that it is going to spew out. In this sense, R is very intuitive. But quite possible that you may not be interested in examining every plot that comes out of the regression model. So if you want the first plot in that sequence, you will say which equals 1. If you want the second plot, you will say which equals 2. If you want two plots in sequence, you will put them accordingly in a frame. In this particular case, we are interested to graph the residuals and the predicted values, and you can immediately get to see that the residuals and predicted values are given. It is quite obvious that the residuals have got a heteroscedastic pattern, that they're not exactly normally or not distributed without a pattern. There is a pattern that you can discern here. That is, as the fitted values are increasing, the residuals are also getting more widely dispersed. The second property of a regression model is the analysis of variance. In order to get the ANOVA table for a linear model in R, you type ANOVA table, then type ANOVA, and then put within parentheses the object in the form of a parameter of that function, the object of linear model. So you see that you need to pay good attention to the object which is created by the linear model. So this gives you the ANOVA table, and the ANOVA table will put up. Here is the ANOVA table, or the analysis of variance table. It gives you the response variable, which is depression. And then you can see the weight and the residuals that come out of this. You can see the degrees of freedom, in this particular case 1 and 8. You can note the sum squares. Okay, so ANOVA works on the principles of sum of squares, and you can read off the p-value from this particular table. Based on the ANOVA table itself, you can work out the R-squared, both the adjusted R-square as well as the R-square for the model. The R-square is actually the property of a model which explains how much in the variability of the outcome variable can be explained by the explanatory variable. In this particular case, as it turns out, it's about 64% in the variation in the outcome variable can be explained by the explanatory variables, but an adjusted R-square, which is a more accurate R-square because it takes into account the degrees of freedom, you see that about 60% is explained by the explanatory variable, which is the weight of the roller, of the outcome variable, which is the depression on the ground. So we stop here, and so before we get into the next phase, which is part 2 of the regression model, let me repeat and summarize what we have learned. We have covered some very basic notions of conducting linear regression of two variables in R. We have seen you can set up a single variable linear regression, which basically means that we have got one outcome variable and one explanatory variable here. We got some ideas how you can interpret the parameters in simple linear regression using R. The idea is this, that you will save the linear model itself in an object, and then you will do this, and you can test some outliers, influencers, etc. But we're going to take a look at this in the next phase. So thank you very much for paying attention.
Welcome back. We had just learned that you can actually use two variables together to set up two continuous variables together to set up your very simple linear regression model. When we were working with this, we learned that sometimes you can have points or you can have observations that can actually influence or lie so far out that can often distort the relationship between the predictor and the outcome variable. And therefore, as an analyst, you need to find out what those points are, what is the correct configuration of the relationship between the explanatory and the outcome variable, and how do we find those things out. So these are some of the more tricky bits, if you will, of setting up a linear regression model. And while this is a good motive for more complicated work, it is good to be aware of these right at this stage. So here it is that we're going to learn about some of these things in the more complicated stuff. For example, we'll learn how to create 95% confidence interval bands around the beta estimates, around the slope parameters, and how to examine the outliers, etc., etc. So this is the bit that we're going to cover here, right? Keep learning, get up your RStudio and datasets, and let's get cracking. Thank you.